We are in section 6.2, talking about applications of the normal distribution, and we're ready to start talking about the second kind of problem in this section, the range or cutoff scores for a certain percentage of values. First of all, we've been working with this formula for z-scores that lets us convert any number, any x, to a z by taking that x minus the mean divided by the standard deviation. Now you can use your powers of algebra to solve that equation. So you could take this equation, multiply both sides by sigma, add mu to both sides, and transform it into x equals z times sigma plus mu. So when you look at it that way, it's a formula converting z into x. So if you start with a z, this is how you can get an x. Now, in what we're going to be doing here are the steps that we'll go through. You don't absolutely have to do this, but it can help you to understand and visualize what's going on if you start by drawing a bell-shaped curve and labeling the area that the problem asks about. Now we're going to need to figure out the area under the curve to the left of the cutoff score. Sometimes that's what you're asked about. Sometimes it isn't, and you have to figure that out from what you're asked about. We'll see examples of that. And then you're going to either go to table E, or you're going to use the invnorm function on a calculator or something like that to find, well, the calculator could take you directly to the final answer, and I will show you that. But if you're using table E, you'll get the z-score for the area that you started with, and then you'll convert that z-score to an x using that formula. So let's see how this works in an example or two. So we're back with our test where the scores are normally distributed, the mean is 100, the standard deviation is 15. Now the question is, what's the cutoff point for the top 10% of the scores? That is, what's the score for which 10% of the people are above, and that would mean the other 90% are below that score. The cutoff score that separates the top 10% from everybody else. Notice this is kind of the reverse of the kind of thing we were doing before. Instead of asking, what's the percentage of x's that are greater than 136, it's asking the percentage of x's that are greater than what is 10%. Okay, so we've got our mean of 100 and our standard deviation of 15, and we've got our assignment here to find the cutoff point for the top 10% of the scores. If you draw a bell-shaped curve, the top 10% would be over here on the right, where the numbers are biggest. Top means biggest, and 10%, I've marked off this shaded region that makes up about 10% of the whole thing. So we want to know where this cutoff point is that separates off this top 10% from everybody else. So the area of this shaded region should be 10%, and what we need to know is the area to the left of that cutoff point, the area over here. So if this is 10%, what's this? 90%, yeah. We could also write that as 0.9000. It's an area, so if you're used to the way that the table is set up, the areas are those numbers in the middle of the table that are given to 4 decimal places, like 0.9000. So if we are going to be using the table, we turn to the table and we look through the table in the middle where the areas are to try to find the closest thing we can to 0.9000. Okay, I see a 0.9015, and then right before that is a 0.8997. So 0.9 exactly would be somewhere in between those two, but it would be closer to 0.8997. That's just 3 10 thousandths away instead of 15 away. So that's the closest area I could find on the table to exactly 0.9000. And can you see what z-score that belongs to? That's where z is 1.28. The first two digits are 1.2, and the hundredths digit is 8. So we're going to put in 1.8 for the z, and 15 for the sigma, and 100 for the mu, and we get 1.28 times 15 plus 100 comes out to be 119.2. So that is the answer. 119.2 is the cutoff score for the top 10%. 10% of the scores are above that, the other 90% are below that. Now suppose we wanted to do this with the graphing calculator. Here's how we do that. Go to the Distributions menu and go down and select InvNorm, the third thing on the list. And if you have the kind of calculator that pops up with a little screen, we're going to give it 3 numbers. The first is where it says area, and that has to be the area over here on the left, to the left of your cutoff point. So that would be 0.9000 or just 0.9. And we can go ahead and give it the mean 100 and the standard deviation 15. And it gives us the answer 119.2. We could use this website. Make sure we're selecting normal distribution. The mean was 100. The standard deviation is 15. And I could either ask for the inverse probability where x is less than 90%, or where x is greater than, and put it in as 10%. So I'm going to do it that way because that's the way the question was originally framed. We want the probability that x is greater than whatever that score is to be 10%, or the percentage to be 10% above that cutoff score. So with that selected, I'm just going to hit calculate. It shows us the graph, and it gives us the answer here in red. The answer is 119.2. Okay, let's try one more example. A reading program is to be administered to the bottom 5% of the students in the district based on the scores on a reading achievement exam. If the average score is 122.6, find the cutoff score that will make a student eligible for the program. The standard deviation is 18. Assume the variable is normally distributed. So here's what we're looking for, the cutoff score that separates the bottom 5%. Bottom would be over here on the left where the numbers are lowest. Separates the bottom 5% from everybody else. So here the question is, what is the percent, what's the cutoff score so that the percent of numbers that are below that cutoff score is 5%, 0.05. If we use the table, we're going to be looking for 0.05. That we were already over on the left, so that is what we're looking for, is the area. Now I see a 0.0505 and then a 0.0495. 0.05 exactly would be somewhere in between those. In fact, it would be halfway in between. It's about equally close to those. So we could take the z for negative 0.0505, which is negative 1.64, or we could take the z for negative 1.65, or we could just take what's halfway between those. Halfway between negative 1.64 and negative 1.65 would be negative 1.645. So any one of those would be close enough. If you used either one of those, negative 1.64 or negative 1.65, or what's halfway between them, negative 1.645, any one of those is close enough. I'm just going to go with negative 1.645. So I'm going to put that into my formula. X equals negative 1.645 for my z times 18 for my sigma, my standard deviation, plus 122.6 for my mu, my mean, and that comes out to be 92.99, or basically 93. So essentially anybody who scores below 93, that puts them in the bottom 5% and they're eligible for that special program. If we did it on the calculator, we'd ask it for inv norm. We'd give it 0.05 for the area, because that's the area over to the left below our cutoff point. We'd give it 122.6 for the mean and 18 for the standard deviation, and it would give us 92.99, or about 93. Now, all of these problems depend on having a situation where we're dealing with a variable that is normally distributed. So, how do you know whether that's true or not? Well, that kind of goes beyond what we're covering in this course. Now, one way you could do it would be to go out, gather a bunch of data, construct a grouped frequency distribution, draw a histogram or a frequency polygon for your data, and see if it looks bell-shaped. See if the shape of your graph is high in the middle and symmetric and like it's supposed to be for a normal distribution. And there are more sophisticated tests that you can do. You could use statistical software and put in a bunch of data into the software, and it has ways of testing how close that is to being normally distributed. So that really goes beyond what we're officially covering in this course, but it is something that a statistician would have to consider, because the kinds of things we're talking about in this section really only work if we are dealing with something that is at least approximately normally distributed.